let's pick up where we left off before the test. So far, we've been looking at the analysis of the systems in the time domain. And it was either continuous time or discrete time. Now we have to look at the other domain, which is the frequency domain. And we're going to first look at analysis of the systems in the frequency domain, first continuous, and then we're going to look at the same for the discrete systems. Analysis of the systems in a frequency domain sometimes is referred to as Fourier domain analysis, based on because all of the frequency tools that we use are coming from the Fourier analysis. And what I'm going to do today is just review briefly Fourier series. I know you've seen it before, but I'm going to try to go over it and organize it so that it fits this particular course. So today I'm going to, as I said, talk about Fourier series. Fourier series are dealing with periodic signals, and they actually teach us that we can build every periodic signals with a proper set of discrete sinusoidals and cosine components. So let me introduce it first, and you'll see these properties in different forms. So the starting point is we talk about periodic signals. And if x of t is periodic, formal definition is that x of t plus nt0 is equal to x of t for every n. It's not for every n, for n equal 0, plus, minus 1, and so on. So n needs to be integer. So if x of t is periodic, I can identify a certain constant value that I call t0, for which x of t plus integer multiples of that constant t0 is the same as x of t. This t0 here we call period of x of t. Now that's mathematically really what when we try to describe it in a less formal way, the signal repeats itself after some t0, right? And if you look at the interval t0, on the signal, it goes through the same value for every point on the signal. Now, if I have a signal that has these properties, what does Fourier series tell me? It tells me that every signal that is periodic can be decomposed into a series that has the following form. So every periodic signal may be decomposed in form given by and here's the form. I'm going to say here x of t is equal to a0 plus sum when n goes from 1 to plus infinity an cosine 2 pi f0t plus bn sine of 2 pi f0t. Now, in here, f0 is equal to 1 over t0. t0 is called period, as I say here. This f0 is called fundamental frequency. And then these coefficients in this expression here can be calculated in the following manner. A0 is calculated as 1 over t0 integral over t0 x of t dt. An is calculated as a 2 over t0 integral over t0 x of t times cosine 2 pi f0t dt. And this coefficient bn is calculated as 2 over t0 integral over t0 x of t sine 2 pi and f0 t dt. So the statement of the Fourier series says, if I have a periodic waveform, x of t, then I should see this periodic waveform as nothing but a series of the sinusoidals that are arranged in a particular way to build this waveform. What is really remarkable here is that these sinusoidals are having really distinct frequencies. They're not of any arbitrary frequencies. Their frequencies are integer multiples of what we refer to as fundamental frequency. Fundamental frequency is 1 over t0. So you don't need some sinusoidals. You know exactly which sinusoidals you need. You need the ones that have frequencies which are integer multiples of the fundamental frequency. So it's a tremendous insight, right, for electrical engineers and some other engineering professions alike. Over time, you actually condition yourself to see the entire world as built of sinusoidals, right? I usually say that into all of my classes. You put Fourier series glasses, and all of a sudden the world is built out of sinusoidals, right? And that's how this analysis works. And you will see a lot of times it is very convenient to see the world that way, you know. And there are other examples. If you think about people that are dealing with light, right? They understand that the light is built out of different waveforms of different frequencies, right? And they are looking the light through a prism where you can see those frequencies separate. We tend to do that with signals too, because what we will see in context of this class, we will find out that linear systems actually see the signals that way too. And they affect different portion of the signal, what we refer to as signal spectra, in a different way. So all of that is going to follow. For right now, let's just look at a simple example. And I wonder if anybody has another one of these. I know you frequently do, because I left the good one upstairs. Oh, okay, for one Thank you so much. So let's go through an example. This is the same as your example 6.1 in your textbook. It looks at the signal that is of this nature. This is 0. This is pi, 2 pi, 3 pi. And here kind of falls, and then does this, does this. In every one of, in this period here, it is e to the minus t squared over 2. So that's a signal that you might have. Anybody who worked with a scope, you know, or doing some electronics, you see these kind of signals all the time. Right? So the question is, I notice the signal is periodic. What is the period of this signal? It's pi. It's pi. So the question is, let's go through the mechanics here and decompose this signal into the building sinusoids. So we start, you know, and I always, in problems of this nature, I always use that as an opportunity to rewrite this, and I suggest you do the same, because it kind of sets what is it that you need to calculate, plus Bn sine 2 pi NF0 t. And then we first identify what is the period, or what is the fundamental frequency. Fundamental frequency is 1 over period, which in this case is pi. So your fundamental frequency is 1 over pi. And then we go through the steps. Step 1 is always going to be calculation of A0. And the formula says this is 1 over period, E0, integral over period times x of t dt. In this case, this becomes 1 over pi integral. Now, the question is from where to when integrate. That will come with naturally with you doing several problems. But the formula says here, and this is what it means when I say integrate over t0, any length of t0 is fine. So you tend to choose the one which is easier to calculate. In this case, I'm going to choose from 0 to pi. And then in that interval, the function is e to the minus t squared over 2. Sorry, why do I put t squared? Let me just put this 2. T over 2 dt. And to make this evaluation easier, I'm going to divide by 2 and multiply everything by 2. So the A0 here is 1 over, or rather 2 over pi. Integral of e to the minus t over 2 dt over 2 is e to the minus t over 2. But because of the minus, I'm going to switch the boundaries here. So, and then when you substitute these boundaries, this becomes 2 over pi. When I substitute 0 here, this is 1 minus e to the minus 1. So that's the value. And, oh, sorry, this is pi. So pi over 2. Pi over 2. And when I substitute the value, this is 0.5443. Okay? So that's A0. The step 2, you calculate your ANs. The formula says this is 2 over T0, integral over T0, x of t times cosine 2 pi n f0 t dt. Notice here that you have n that appears as a parameter, so when you carry this integration, there will be, you will end up with a function of n, something that depends on n at the very end. It's not going to be a single number. When I substitute this, this ends up being 2 over pi, and then integral from 0 to pi, e to the minus t over 2 times cosine 2 pi n. Instead of f0, I'm going to put 1 over pi t dt. So that's what we need to calculate here. Now that's this is a little bit cumbersome, but let's just what I'll do is I'll shorten this a little bit by giving you the result again. But the way I approach this is 0 to pi e to the minus t over 2. And then you have here cosine of 2 pi and actually 2nt. So this is e to the j 2nt plus e to the minus j or 2nt divided by 2dt. What did I do? Instead of f0, I'm writing 1 over pi because that's 1 over period. Period is pi. Pi and pi cancel, so you have cosine of 2nt. Well, the cosine is e to the j plus e to the minus j over 2. And why do I do that? Because now you can see you can group this into 2 exponentials that integrate very easily. So this can be rewritten now as 2 over, or maybe this 2 and 2 cancels. And the first integral is 1 over pi, integral from 0 to pi, e to the minus 1/2 plus j 2n t dt. And then plus the second one is 1 over pi, integral from 0 to pi, e to the minus 1/2 minus j 2n t dt. Okay. Let's continue over here. So this an is going to be equal 1 over pi from there. And then the first integral is e to the minus 1/2. This minus 1/2 minus j2n t over 1/2 minus j2n, evaluated from 0 to pi, and then plus e to the minus 1/2 plus j2n t over 1/2 plus j2n 0 to pi. Notice there was always minus that went downstairs, and I used that minus to flip these borders, right, of the integration. And this reduces quite nicely. So this is 1 over pi. Upstairs, when I substitute 0, I have 1 minus e to the minus 1/2 minus j2n pi divided by 1/2 minus j2n, and then plus, again, 1 minus e to the minus 1/2 plus j2n pi divided by 1/2 plus j2n. And in this thing here, you see that you have e to the j2n pi. What is the e to the j2n pi? Cosine, but it's an integer multiples of 2n pi. So e to the j2 pi integer brings you where? To 1, right? E to the, so this n disappears from upstairs, and you end up with something that looks like this, 1 over pi. And then if n disappears, the second term disappears, then you have e to the minus pi over 2 here, and e to the minus pi over 2 here as well. So this becomes 1 e to the minus pi over 2. That is up front, and then you have to add these two terms, which is downstairs 1/2 squared plus 2n squared, and then 1/2 plus j2n plus 1/2 minus j2n.
So it should be minus 1/2 square minus 2n square
Where?
in the denominator. No, j square is equal to minus 1. Yeah, right. Sorry, it's right.
This is what is downstairs, the
Yeah.
product of the two. And then
J square is minus 1. That's why
this
minus
goes
1.
here, and then this goes over here. So when you when I did this, so let me see here. I ended up with 1 pi over 1 minus e to the minus pi over 2. And then I have here 1/4 plus 4n squared. And here I have 1, right? If I didn't make a mistake anywhere. Okay. So when you calculate this, this is 0.5443 times 2 over 1 plus 16n squared. And then finally, step 3, this is calculation of the Bn. Bn is given as 2 over t0, integral over t0, x of t times sine 2 pi n f0 t dt. And in this case, this is 2 over pi, integral from 0 to pi, t to the minus t over 2 times sine 2 pi and 1 over pi t dt. And you will proceed in the same manner as in the previous. You will take the sine, make it 2 exponentials, and after a couple of lines, you end up with something that is 0.5043 times 8n over 1 plus 16n squared. So these are your coefficients. Now, once you calculate all of them, then you can put the whole thing together and say x of t is equal to 0.5043 as your DC component, or A0, plus sum, when n goes from 1 to infinity, 0.5043 times 2, 1 plus 16 n squared, cosine of 2nt, and then plus 0.5043, 8n, 1 plus 16 n squared, sine 2nt. Or even more simplified, this is 0.5043, 1 plus sum, when n goes from 1 to infinity, 2 over 1 plus 16 n squared, cosine 2nt, plus 8n over 1 plus 16 n squared, sine 2nt. And that's how you complete this. So that's the Fourier series associated with this waveform. This is, I guess, an example where I had to do all the steps. And this is as hard as it can get, right? It should not get harder than this, except for maybe having a harder time evaluating this integral. But conceptually, these are the steps. You can have at most 3 steps. In the first step, you're going to calculate A0. In the second step, you calculate ANs, and in the third step, you calculate BNs. This form that I have here, it's called Form 1, or basic trigonometric form of the Fourier series. We use 2 additional forms that are equivalent, but somehow give us better insight in a certain situation. So let me discuss these 2 forms. And then what I need to show you is a couple of tricks how you can get out of some of these calculations in specific cases. And this is, as I said, as hard as it can get. A lot of times, depending on what your waveform looks like, you may be able to right off the bat say that some of the terms you don't need to calculate, or you may be able to calculate them just by inspection of the waveform. Oh, wait. All right, so let's introduce alternative forms. Of Fourier series. The second form I'm going to call compact trigonometric form. In this case, we start by saying x of t is periodic, and it can be decomposed as A0 plus sum, when n goes from 1 to infinity, an cosine 2 pi n f0t plus bn sine of 2 pi n f0t. We're going to use the trig identity that we used several times throughout this course already, which says that a cosine of alpha plus b sine of alpha is going to be equal to square root of a squared plus b squared times cosine of alpha minus arctangent b over a. Which tells us that if I have a sine and cosine, of the same frequency, and I add the two, I'm going to have the component, which is the cosine of the same frequency, just shifted in phase and possibly modified in the magnitude. In other words, when you add sine and cosine, you actually end up, there is no sine and cosine per se. It's just this one cosine that's shifted, you know, based on a, and then it became sine, right? By shifting by pi over t. So if I use this here, then I can rewrite my x of t as a0 plus sum, n goes from 1 to infinity. And you notice that these two have the same argument, so I can rewrite this as a square root of an squared plus bn squared times cosine of 2 pi n f0 t minus arctangent bn over an. Right, so I have shrunk this form somewhat, and then at that point I can define C0 as being the same as A0, and then Cn as square root of an squared plus bn squared, and then theta n as this whole thing minus arctangent of bn over an. So with that in mind, with those definitions, I can say this x of t is equal to C0 plus sum when n goes from 1 to infinity, Cn cosine 2 pi n f0 t plus theta. This form, in my opinion, is the most insightful. It actually tells us exactly how the signals are being built, periodic signals are being built. You see that you have to have cosines of that are having frequencies that are integer multiples of the fundamental frequency. But to build a signal, you have to align these cosines in two ways. You have to phase them properly, meaning that they need to be of appropriate phase, or which is equivalent to shifting them along the t-axis. And then you have to scale them properly, which is essentially this thing here. So you have to have a proper scale for a given cosine and proper phase shift. And then when you put them together, they're going to magically align to form the signal that you start from, the one that we did the example for. This C0 is also a cosine of what frequency? What is n in this case?
Zero.
Zero, right? So if I put, so I can essentially rewrite this in one more way, but I don't recommend it. You can say Cn cosine 2 pi n f0 t plus theta n. And you just know that for n equals 0, theta n is equal to 0, and Cn is equal to this C0. So it is really sum of the cosine, but we have a special cosine, the cosine for which the fundamental frequency is 0, and its phase is also 0, right? So this is just for, I guess, further explanation. The form is this one. Okay, so that's what we call compact trigonometric form. It is very insightful, but there are no direct calculation formulas. In other words, you cannot calculate directly Cn and theta. You have to go the other way. You have to calculate A's and B's and then calculate C's and thetas. There is no direct formula for calculation of Cn and theta.
Excuse me, sir. From this equation, can we infer that the harmonics are always phase shifted?
Yeah, I mean, not always, but most of the time. When you build let's say you have a periodic waveform, and it has a frequency of 10. Then what do I know? I need to go to the signal toolbox here and build a cosine that has frequency 10, well, cosine that frequency 0 first, then cosine with frequency 10, 20, 30, 40, 50, and so on. And then I start putting them together. First I put C0, then I put cosine of the frequency 10, but I have to, phase it properly and stretch it properly along this one. And then take the next one, and this one I phase properly, stretch properly, and then ultimately I build the waveform, right? So the adjustment that you need to do to every one of these components is going to be the magnitude and phase. And we're going to talk about magnitude and phase of individual harmonics that participate in building on the system.
Is it possible to get the resonant frequency of the particular harmonics with respect to our actual frequency with this equation?
I'm not sure I understand the question. Is it possible to do what?
To get a resonant frequency, a resonant harmonic frequency.
What is a resonant harmonic?
THD,
Yeah.
total harmonic distortion.
Harmonic distortion?
Yeah, THD.
THD.
Okay, but that's a completely different issue. What is harmonic distortion? This is if what happens, this is kind of, if you have a nonlinear system, and then you run a sinusoidal through that system, then besides the fundamental frequency, you're going to get all of these other harmonics. Harmonic distortion is defined as the power in harmonics divided by the total power of the output signal. It's a measure of how linear your system is. So that goes into a slightly different area. Here we're dealing with linear systems, so there's no distortion. When I present the sinusoidal to my linear system, what happens to the sinusoidal? What happens to it? Magnitude may change, phase may change, frequency cannot change. So my linear system will never produce additional harmonics. Therefore, there cannot be any harmonic distortion when it comes to linear systems. The truth of the matter is, every system is linear to a certain extent. And then through harmonic distortion, we discuss how linear the system is.
Thank you, sir.
All right, so let's look at the third form. The third form is what we call exponential form. And in this one, we also start by saying x of t is a0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0 t plus bn sine 2 pi n f0 t. And then we start transforming this formula into just exponentials. So how do we do that? We say this is equal to a0 plus sum when n goes from 1 to infinity, an. Instead of this cosine, I have e to the j 2 pi n f0 t plus e to the minus j 2 pi n f0 t over 2. And then plus bn e to the j 2 pi n f0 t minus e to the minus j 2 pi n f0 t divided by j2. What did I do here? Nothing really special. Cosine is this, sine is this, right? So there's really nothing fancy about this. But at this point, I can start reorganizing this formula. And I can say this is a0 plus sum when n goes from 1 to infinity, a n over 2 plus bn over j2 e to the j 2 pi n f0 t. What is it that I'm doing? I'm grouping everything with this exponential here. From the first sum, I have an over 2. From the second sum, I have bn over j2. And then plus the next term is going to be n goes from 1 to infinity, an over 2 minus bn over j2 e to the minus j 2 pi n f0 t. So I have three terms. I have one constant term and two sums that I need to deal with. Now this simplifies a little bit. And I can say now x of t is equal to a0 plus 1/2 sum when n goes from 1 to infinity, an minus j bn times e to the j 2 pi n f0 t, and then plus 1/2 sum n goes from 1 to infinity, an plus j dn e to the minus j 2 pi and f0 t. And here I can really simplify this and say this is sum when n goes from minus infinity to plus infinity dn e to the minus j 2 pi and plus j 2 pi and f0 t, where d0 is equal to a0 and then dn is equal to 1/2 an minus j dn for n greater than 0 strictly, and dn is equal to 1/2 an plus j dn for n smaller than 0. So what is the conclusion here? Well, this is yet another insight. Remember, we said that that we can build a periodic waveform out of the cosine zone. But then you say, wait a minute, cosine is built out of exponentials, right? Therefore, I can build the waveform just as an exponential. And what I need all the exponentials that have frequencies that are integer multiple of the fundamental frequency. But in this case, this n can be both positive and negative. And that kind of introduces the notion of the negative frequency. But there's really no negative frequency. It's just that two of these combined give you one cosine, one with the positive NF0 and one with the negative NF0. Together give you one cosine that you use to build the waveform here. Now, this one has a set of calculation formulas. For n equals 0, we get d0, and this is 1 over period t0, integral over t0, x of t dt. Why is that the case? You can see d0 is the same as a0. So the calculation formula that we use for a0 would allow us to do that allow us to use it here for d0 as well. dn is going to be 2 over t0, actually 1/2, and then calculation formula for an is 2 over t0, integral over t0, x of t, e to the, sorry, not e, cosine 2 pi n f0 t dt. So this is your an. And then minus j 2 over t0, integral over t0, x of t times sine 2 pi n f0 t dt. Okay. What did I do here? Nothing. Just took an from how the calculation formula for an and put the calculation formula for bn over here. In these equations, n is positive. So let me just put it here. N is positive. So dn ends up being, you see 1/2 and 1/2 canceling. So I have 1 over t0, integral over t0. And don't let me write everything. We're good enough at this point. We can do a lot of it, but in our heads. X of t comes here as a common. And then you have cosine of this minus j sine. And you can see cosine minus j sine is e to the minus whatever is the argument. So it's e to the minus j 2 pi n f0 t. So that's the calculation formula for for n greater than 0, and then see that we can substitute n smaller than 0 and get essentially the same formula. Let's see what happens here. N smaller than 0, dn is 1 over t0, integral over t0, x of t cosine 2 pi n f0 t dt plus j t over 0 integral 0 x of t sine 2 pi and then 0 t dt. And then you can see that this is 1 over t0 integral over t0 x of t. And since I can write this now as e to the j 2 pi and 0. Right, so that's for n smaller than 0. And since you can write this as the same way as this, just work with the positive n and then put the minus. Right? So in general, I get the formula. dn is equal to 1 over t0 integral over t0 x of t e to the minus j 2 pi and f0 t d. And that's the calculation formula for dn. So if you look at it now, this one and this one, they're essentially the same formula. When if I substitute n equal here equal to 0, then I get that d0 is exactly to this, equal to this, right? For n equals 0, this formula for dn morphs into this one. You can see that, right? Because if n is equal to 0, this e to the 0 is equal to 1, and you essentially end up with a single calculation formula here, saying that dn is equal to 1 over t0 integral over t0 e to the j, x of t e to the j minus j 2 pi and f0 t dt. So you say that x of t is equal to this, and dn is calculated based on this thing here. Now this seems like the simplest, right? The truth is it is the most compact. It's not the simplest. Because in the case of an and bn, you have, or in case of a's and b's, you have essentially two real integrals, one for a and one for b. Here you have one integral, but it's for complex. It's a complex integration. And as soon as you start doing problems, you will see that the most common thing that happens is this integral ends up being two integrals that you need to calculate separately anyway. So you cannot really double cross the nature. You always end up doing the same things. But this is the most compact form, and it's our favorite form when we do derivations and all the math, because it's just the smallest writing. It's the shortest to write stuff. But all three of these are used. The first one is the basic one, and essentially, if I'm asked to do Fourier series, I will always go to the first form, right? Just the calculation of it. When you do the calculations, you're least likely to make mistakes when you do the first form. Second form, I would say, is more insightful. It tells you how the components are arranged to form the particular waveform. And the third one is the most compact, and you kind of use it mostly in derivations, proofs, and just trying to show different properties. So let me now summarize everything in one spot, and you can kind of note that page in your notes so that you always go through when you do the calculation.
Hey, Professor, why do we ignore for the n less than 0 where it's a positive e to the j? In general, we only use the n greater than 0.
No. It's this thing here. dn is equal to that, right? And then you, when you do the calculations, right? You can see that for positive zeros, you put the minus here, right? For positive n's, you have a minus here. For negative n's, you have a plus here, right? But it's essentially the same formula, right? Let me just, because you can put here, you can do this, right? You can treat this as minus, and then put here minus, okay? And then this ends up being the same formula as this one, right? Because you see this is exactly the same, right? So it's the same formula that you end up calculating. I'll go through examples, you will see what happens there. But it's essentially, everything boils down to this one formula that you need to calculate. All right, so let me summarize everything here so that because here's what you're doing. Look, maybe this will help. N goes from 1 to infinity, right? So when I'm merging here, I'm merging this into one summation when n goes now from minus infinity to plus infinity. So instead of going here over positive n's, I can go over negative n's, but then I need to switch the signs of n in this equation, and this equation, and this equation. Okay. You got it. This sum here is, one step is missing here, and that step is x of t is equal to a0. That's fine. But then I have sum when n goes from 1 to infinity, an minus j bn, e to the j 2 pi n f0t. And then the third sum, I can write sum when n goes from minus infinity to minus 1, a minus n minus j b minus n e to the minus j 2 pi n f0t. Right? That's actually plus. Sorry, plus, right? Because if I go here over positive, I have to make minus n, minus n, minus n here, right? And then if you look at this guy here, then this is d minus n. This is d for negative n. And d for negative n smaller than 0, ends up being a minus n, which is, I guess here, there's 1/2 missing, right? So it's going to be 1/2 2 over t0, and then a of just integral over t0 x of t times cosine 2 pi n, but minus n f0t dt, and then you have minus 2 over t0 integral over t0 x of t times sine 2 pi, again minus n times f0t dt. And then you can see that in this case, this ends up being the same as 1 over t0. A of minus n is an. And then, sorry, this was plus, right? Plus from here. Plus. Plus, and then there's plus here. And then b of minus n is minus b of n, right? So this becomes minus j b of n. And then look at it formally, this is the same as this. So now you can actually see that the same formula is valid for all n's. The trick is that there's one step missing here. When I switch this integration, or this summation, not going from 1 to infinity, but from minus infinity to minus 1. Okay, so let me summarize everything. So summary. So there's a form one. This is our trigonometric form. And it says that x of t is equal to a0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0 t plus bn sine 2 pi n f0 t. So that's the series, right? And then the series is accompanied with calculation formulas that tell you how you derive these coefficients A's and B's. Here, f0 is 1 over t0. A0 is calculated as 1 over t0, integral over t0, x of t dt. An is calculated as 2 over t0, integral over t0, x of t, cosine 2 pi n f0 t dt. And then dn is calculated as 2 over t0, integral over t0, x of t, times sine 2 pi n f0 t dt. So this is a very useful formulation because it has all the calculation formulas that gives you the coefficients. The second form is a compact trigonometric form. And in this form, we have that x of t is equal to c0 plus sum when n goes from 1 to infinity, cn cosine 2 pi n f0 t plus theta n. There are no direct calculation formulas for this form. We have to calculate still a's and b's, and then you get that c0 is equal to a0, cn is equal to square root of an squared plus bn squared, and theta n is equal to minus arctangent bn over an. So that's the second form. Also from here, you can go back and you can calculate an is cn times cosine of theta n, and bn is equal to cn sine of theta n. So this is how you travel back and forth between form 2 and form 1. Obviously here, a0 is equal to c0. And then the third form is exponential form. This one is notationally the shortest. X of t is equal sum when n goes from minus infinity to plus infinity, dn e to the j 2 pi n f0, and dn is calculated as 1 over t0, integral over t0, x of t e to the minus j 2 pi n f0 t dt. There's t missing. And the transition between these you can say that dn is equal to an minus j bn. That's how you calculate d's if you know a's and b's. And then if you know d's and you want to calculate a's and b's, then an is equal to dn plus dn complex conjugate, and bn is equal to dn is j bn minus dn complex conjugate. So that's the way how you go back and forth between the third form and the first form. And then the last one, so this is, the last one is between these two forms. You can say that Cn is equal to 2 times Dn, and theta n is equal to the angle of Dn, and backwards Dn is going to be equal to 1/2 Cn cosine theta n minus j Cn sine of theta n, and which is the same as 1/2 Cn e to the j minus j. So that's how you calculate these from C's. So that's all in one spot. Okay, a lot of formulas, but they're not really hard, you know. The question always is, should you learn them by heart? And my answer is, why not? Because nothing bad is going to happen to you if you learn them. And if you don't, you know, you're always going to be searching for them. And that's the dangerous thing on the exam, because you lose time. So my suggestion is try to learn them if you don't know them already. You know, they're not that difficult to learn. But it's not required. I mean, for the exams, you're always going to have a sheet with the formulas there. It's just that, as I said, nothing bad happens to you if you learn this stuff.
Sir, when we have trigonometric, why we went to compact? Any advantages?
At this point, I cannot really justify it. At this point, it just looks like an exercise, mathematical. But you will see when we start talking about signals that are non-periodic, then we'll discover that the signal does not have to be periodic to be built out of sinusoids. Every signal is built out of sinusoids. And the way for us to show that is we're going to actually use this form. And what will happen is this form will transform into what we all know and love and call Fourier integral. Right? So, as I said, usually this form is most convenient when you try to prove stuff and derive, and in most of the theoretical textbooks they are using this form. I think you pick a lot of communications books, they just do this because they tend to be highly theoretical and derive things and prove things and so on. But in reality, you know, when you start working on a bench with I guess scope, and when you start working with the hardware, you don't really see this right away. What you see is this guy. Right? You see that the signal is built out of a whole bunch of sinusoidal, each one having a magnitude and phase. Right? So that's what you see on a real equation. But nevertheless, this one is really important for us, and we're going to use it quite a bit. But I'll go back to this. You know, you will see that right now I have no basis to say you need this one. So, as you probably guessed, from a student standpoint, right? And also, you know, I'm just joking when I say student, but the biggest practical issue here is calculation, right? You are given this intuitively. It's easy to understand what's going on, right? You have a periodic waveform. It's built out of sinusoids. That's the end of the theory, right? That's where the actual practice starts. And the practice is, well, what are those sinusoids? And you see that each one of these leads to a lot of calculations that need to happen for you to determine the magnitudes and phases of those sinusoids. So there are some practical things that you should know that help you in calculating, that help you in determining what those sinusoidals are. And in these instances, we're going to use symmetry. Symmetry is our good friend and will help us identify what we need to calculate and what we don't need to calculate. So we call this like a physical insight. And symmetry. So first, let's talk about A0. A0 is calculated as 1 over T0, integral over T0, x of t dt. What is A0? What's the physical meaning of it?
component?
It's a DC component of a signal. So if the signal does not have a DC component, I can discard calculation of A0. I don't have to do it. If the signal is the same above the x-axis and below the x-axis, it does not have a DC value, then you don't have to calculate A0. Even in cases where you calculate A0, my advice is guess what it needs to be. A lot of times you can eyeball the signal and you can say, okay, its DC component is between 1.5 and 2. And then you go and calculate, and then you look what you end up with, and you compare it against your guess. And they should be close, because we are pretty good at guessing DC values, right? You can look at the signal and kind of eyeball and say it's approximately here. And we're pretty good in messing up the integrals too, right? So use this guess of yours to check the final value of what comes out of the integral. If these two don't align, then you probably messed up the integral. You need to go in and see where was that 1/2 or something that is missing. So that's the first hint. The second hint is if you look at x of t, then this is what we know. It's sum when n goes from 1 to infinity, an cosine 2 pi n f0t, plus sum when n goes from minus infinity to plus infinity, dn times sine 2 pi n f0t. Now this part here is built out of even functions. So this is an even part, or even building blocks. This part here is odd part. Okay? So, so if the function is even, there is no odd part. And therefore, Bn is going to be equal to 0 for every n. So if you look at the function, it has an even symmetry. There's no need to calculate Bn's. They're going to be 0 for every n. Likewise, if x of t is odd, there's no even part. And all of your an's are going to be equal to 0. Okay? So this is tremendous help to us, because if the function has any kind of symmetry, you're cutting your calculations in half.
The Bn summation goes from negative infinity to infinity?
No, sorry. 1, of course. 1. Yeah.
Give us all. Give us all.
I can't hear you.
Give us all.
Give us.
Like we can stop here.
We can start. Yeah. Let me give you homework, and I agree. I'm up since 6:30, so
We have to continue.
let me just give you homework problem. And 6, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. So these are the problems. When we come back, I have an example here. So when we come back next time, I'm going to go through the whole example and do all 3 forms so that we have an example of how the calculation happens for all.
Thank you, sir.
Thank you.